Today we're going to work on balancing equations. And when we're balancing equations, we have to make sure that we understand the difference between a subscript and a coefficient. A subscript are the small numbers down below. These numbers are here for stability purposes. A coefficient is the big number out front. This coefficient is there to show the conservation of mass. If I am counting the atoms, I would need to multiply a coefficient all the way through, whereas a subscript, I would only need to consider how many of each atom are present. So here I would have 4 aluminums and 6 oxygens. In terms of seeing a visual of what this means, if I have 2 groups of aluminum, this is telling me how many groups I have. The subscripts are telling me how many atoms are bonded together. So if I have aluminum, aluminum has a +3 charge and oxygen has a -2 charge. So in order for aluminum and oxygen to be happy together, I would need 2 aluminums and 3 oxygens. That is telling me how many are bonded together. So if my aluminum is a closed circle and my oxygen is an open circle, it's telling me that I have 2 aluminums bonded to 3 oxygens. This number out front is not anything to do with stability. Instead, that number out front is telling me how many groups of Al2O3 I have. So 2 groups containing 2 aluminums and 3 oxygens. All right, so we are going to look at an example of magnesium reacting with oxygen. Magnesium is Mg, it is stable on its own, and oxygen is O2. The oxygen source is going to be the air. We have magnesium and oxygen. I am going to add a little bit of heat to get the reaction going. And when I add heat to the magnesium and give it the little energetic push that it needs, the magnesium will begin reacting with the oxygen in order to create something new. The question is, what is that new substance we made? We started with a metal, and now we have a brittle white solid. In order to figure out what that brittle white solid is, we have to consider first stability. How can magnesium and oxygen be happy together? So magnesium, I know, has a +2 charge. Oxygen has a -2 charge. That means that the only way that magnesium and oxygen can be happy together is if one magnesium is connected to one oxygen. Stability is first and foremost. Once we have a stable compound, now we have to take a look and make sure that we have not created or destroyed matter. The law of conservation of mass says that matter cannot be created or destroyed in a chemical reaction. So I'm going to count my number of atoms going in and my number of atoms coming out. Magnesium and oxygen appear on the reactant side, and they also appear again on the product side. I have 1 magnesium going in and 2 oxygen atoms coming back out. I'm going to go over to the product side. I have 1 magnesium coming out and 1 oxygen. It appears that we have destroyed an oxygen, but we know that nature will never let that happen, so this cannot be written correctly. Once we have made all of our atoms stable, our only option is to add coefficients in front in order to change the number of molecules going in and coming out. So if I have 2 oxygen atoms going in and 1 coming out, the only way to fix this is by putting a 2 out front. I cannot change the subscript. So 2 magnesium oxides. So 2 magnesiums come out and 2 oxygens are now coming out. In the process of fixing my problem with the oxygens, I've created a problem with the magnesium. I can't put 1 magnesium into a reaction and expect 2 to come out. So the only way to fix this is to put a 2 out front. That 2 is going to multiply through, but only to my magnesium, not to my oxygen, because they are separate molecules separated by a plus sign. So now, this reaction shows not only stability, but it also shows the conservation of mass and the fact that everybody is happy. If I were to model out what this looks like, magnesium, I have 2 separate groups of magnesium shown by the coefficient out front. I have 1 oxygen molecule that contains two oxygens bonded together. On the product side, this is telling me I have two groups of MgO. So Mg and O are connected together, and there are two groups of them. When I am finished, the number of magnesium atoms and oxygen atoms going into the reaction should match exactly what came out. All right, let's do another example that's a little more complex. When an equation is written for you and the reactants and the products are given, you can assume that these are all stable. That means that they are zeroed out and each of the elements is happy. They have a full number of valence electrons. What I'm going to do is begin by counting my atoms on the left side of the equation and on the right. I can't create or destroy matter, so I am going to list all of the atoms that go in, and I'm going to copy that list over to the product side because I can't create or destroy or lose any different atoms. All right, I have two Ks, I have one oxygen, I have one aluminum, and I have three chlorines. Over here on the product side, I have one potassium, three oxygens, two aluminums, and one chlorine. Clearly these lists don't match. That means that this equation is not correct. It would not occur like this in nature, so we have to figure out what would happen. In order to do that, we cannot adjust any of the subscripts. We can only adjust coefficients. So it does not matter where you start. You are going to start with one of the atoms that does not match. It appears that two Ks go in and only one come out. So what I'm going to do is find the K on the side of the equation that has less. So my product side has less, find the K in the equation. I cannot add subscripts. I'm only allowed to add coefficients. So I need to figure out what coefficient I need to put here to give me the two Ks that I want. That coefficient is going to be a 2. But when I put the 2 there, it multiplies through the entire compound, so I'm going to change my list to reflect that coefficient that I added out front. I now have 2 Ks, but don't forget I also have 2 chlorines. Now my Ks match, but none of my other elements do. Remember that it's going to take several times of going back and forth before you get these to balance. Oxygen is my next one that doesn't balance. In order to make the oxygen match, I'm going to go to the side that has less, the reactant side. I'm going to find the oxygen. I cannot add subscripts because subscripts are determined by stability, and this is already a stable, happy compound. So I'm going to put a coefficient out front. In order to get the 3 oxygens that I need, I'm going to have to put a 3 here. That 3 is going to multiply through the entire compound, giving me 6 Ks and 3 Os. I'm going to change my list to reflect that. Notice that in fixing my O's, it messed up my K's. That is okay. This is going to happen. We're going to have to just keep going back and forth until they all match. My aluminum, I have 1 aluminum going in and 2 coming out. That is not correct. They have to be the same on both sides in order to show the conservation of mass. So I'm going to find my aluminum on the side that has less, the reactant side, and I'm going to put a coefficient in front. In order to get the 2 aluminums that I need, I'm going to need to put a 2 out front. That 2 will multiply through the entire compound, giving me 2 aluminums and 6 chlorines. My oxygens and my aluminums match, but my chlorines and my potassiums do not. It does not matter where we go next, but it is perfectly okay to say, you know what, putting a 2 in front of the K did not work. Since I have 6 Ks going in now, I'm going to erase this and make this a 6 so that my Ks match. That 6 multiplies through the whole compound, giving me 6 chlorines as well. As soon as both sides match, this is a correctly balanced equation that shows stable reactants and products, as well as the conservation of mass. No atoms have been created or destroyed. So what does this equation mean? Well, this means that 3 molecules of K2O react with 2 molecules of AlCl3 in order to produce 1 molecule of Al2O3 and 6 molecules of KCl. All right, equations can become more complex to balance, but the process will be the same always. So here is a little more complex reaction in which we have polyatomic ions. When we have polyatomic ions, there are a few tricks and tips that we can use to make this a little bit easier. When we have a polyatomic ion, rather than listing all of the atoms separately, what we're going to do is leave the polyatomic ion together when we're counting. Now, this only works if you make sure that the polyatomic ion, the OH here, goes in and comes back out of the reaction intact. It hasn't broken apart. Here I have phosphate, PO4. The PO4 goes in and comes back out. So I can leave that together and it's going to make the balancing process a little bit easier for us. I have Na. I'm going to leave my OH together. I have Mg and I have PO4. Again, I'm going to leave those polyatomic ions together when I'm counting. I have 1 sodium, I have 1 OH, I have 3 magnesiums, and I have 2 phosphates as indicated by the number outside the parentheses. When I go over to the other side, I have 3 sodiums, I have 2 hydroxides as indicated by the number outside the parentheses, I have 1 magnesium, and I have 1 phosphate. It does not matter where you start in this process, so I am going to randomly start with the Na, first one on the list. So if I have 3 NAs coming out of the reaction, 3 must have gone in. And the only way I can make 3 go in is by having a coefficient of 3. I cannot change the subscripts because, again, changing the subscripts would change the stability. So this is happy as NaOH. If I want more than 1 Na, I'm going to have 3 of the entire molecule. That 3 is going to multiply all the way through the compound. So now I have 3 NAs and 3 OHs. I fixed my sodiums, but I have messed up some of the other ones along the way. That's okay. Pick your easiest fixes first. So 3 Mg's in and 1 out. I'm going to find my magnesium. And if 3 went in, then 3 magnesiums had to have come out. The only way to fix that is to put a coefficient of 3 out front. That 3 multiplies through the entire compound, which gives me 3 magnesiums. And now, instead of having 2 hydroxides, I'm going to multiply that by 3, and I have 6 hydroxides. My PO4s don't match either. 2 of them went in, and if 2 went in reality 2 had to come back out. The only way I can make 2 of them come back out is by putting a coefficient in front. That 2 multiplies through the whole compound, giving me 6 NAs and 2 PO4s. All right, my magnesiums and my PO4s match, but my NAs and my OHs do not. I originally had a 3 here, but it is perfectly okay to erase the coefficient. And rather than a 3, I can fix this and make both sides match by putting a 6 out front. When I put a 6 out front, it multiplies through the entire compound, giving me 6 NAs and 6 OHs. This is now a balanced equation. So when this reaction happens, I will have 6 NaOH molecules reacting with 1 magnesium phosphate to give me 2 sodium phosphates and 3 magnesium hydroxide.